Hello everyone, I am Humardeep Bosak, a third year undergraduate student from the Department of Aerospace Engineering, IIT Kharagpur. Today, I will be discussing about the derivation of Navier Stokes equation, that is a set of partial differential equations governing the fluid motion, and it is one of the most fundamental equations in fluid mechanics. So our today's topic is derivation of Navier Stokes equation. Okay, so let's begin this by deriving the stress tensor from Cauchy construction. So let me draw the Cauchy construction first. What is it? This is the three orthogonal axes. We draw a tetrahedron element here. Okay, so just ignore that curvy lines. Okay, so this is the tetrahedron element here. Now let's define the axis. This is B, this is C, this is A, and we define the surfaces as one. Okay, another is the origin O. Here my AOB forms a surface like this. My AOC forms a surface like this, and my COB forms a surface like this. Okay, and also there is another surface, that is AOB. So again, so writing like this. Now we define the surface element, that is the surfaces we now define like this, that consider the COB plane, that is COB surface. We consider it as delta A1, the value of the surface. The COA, we consider it as delta A2. The AOB, we consider it as delta A3. And the ABC, we consider it as delta A. Now we define the direction vectors, that is the unit normal outward of the plane. So we want define for the COB plane as in this direction minus A. For COA, we define in this direction minus B. For AOB, we define in this downward direction as minus C. And for ABC, we define as the outward direction as let's say N. It becoming clumsy there, but let's just ignore that. So my delta A is the area element for that surface, and my N is the direction vector. Okay, now let's define a stress quantity. Okay, so we are defining now a stress quantity as sigma. What is this sigma? This sigma is a representative of some force per area. Okay, so let's just do it right here, that we consider a force dF. Let's say this is any surface, particular any force is acting right here like dF. The unit normal is in the direction N. Okay, and let's say this surface is any dA, the value of the area of the surface. So we get dF is equal to sigma of N into dA. This sigma is a stress quantity that's act on the area normal. Okay, so dF is the force is stress into area. dF is the force and sigma N is the stress quantity, or we will construct a different vector, but at later stage, let's just consider it's any stress quantity relating the df and dA. Now you understand that this is not simply any scalar quantity because it has the information of both on in which direction my force is acting, and also it has the information of what is my area normal, that is what is the area normal or n for the dA. So this in totality defines the force dF acting on surface dA with an area normal n related by this stress quantity. So this is, you understand, a surface force that is acting at this surface. So for this tetrahedral element, that is Cauchy element, we now calculate the summation of all the surface forces acting. Let's just calculate that. So what will it be? That is 1 for the outward surface. It will become sigma of n into delta A plus sigma of minus A into delta A1 plus sigma of minus V into delta A2 plus sigma of minus C into delta A3. This is the summation of forces. Now let's understand a different fact about this surface force. Let's consider this is a surface and this is the area normal to that. Consider this as A and B. So what is the forces? Let's say some fluid particles is right here, some fluid particles it's right here. Okay. So what is the force acting on these B fluid particles by the fluid particles at A acting at the interface? We consider it as FAB. In the similar way, the forces acting on the fluid particles at A from the fluid particles at B or by the fluid particles at B, we consider it as FBA. Now, you know from the Newton's third law of motion, we can write it as FAB equals to minus FBA. Very clear this point. Now we fall back to our stress quantity definition. What is FBA in terms of stress and area normal? Okay, so another is that the area here is delta A. So what is this FAB? This FAB is nothing but the area normal that is acting as n into sigma, that is the sigma of n into delta A, and for the opposite quantity it will for the negative normal vector, that is the sigma of minus n, this minus n is coming, and delta A. From there what we can write? We can write sigma of minus n is minus of sigma n. This is an nice simplification for the stress tensor quantity. What we can explain from it, that is sigma n or the sigma function is acting as an odd function. Clear this point? So we now apply this expression into our previously derived expression. So what we can get? We can get this quantity remains as intact. Now for each of the quantities, one minus is coming and we just take it as a common. So it will become like this. We get another expression. Now just understand the orthogonality of vectors. That is, what are the surfaces dA1, dA2? How can we define with respect to the dA? So this is the vector geometry part. That is, in this tetrahedron element, I am again drawing it so it will make clearer. Okay, so this is a very poor drawing. So let's just, this is the n This is the minus a vector right here. So what is this area? How can I find this area? This area is nothing but the area that is acting at that is for the unit normal, which is minus a. So this is simply the projection of this upper or the above triangular surface for this tetrahedron that is joining, intersecting at the three axes, the projection of that surface into, let's say we consider as BC, so BOC plane is the surface element we are interested as delta A1. So what we can write, delta A1 from the dot product rule, from the projection rule, A dot n into delta A. What it will give? When you do A dot n, it will give the projection component, that is some cos theta component, and the delta A is that above triangular area. Apply on that cos theta, and it simply get the projection, that is delta A1. Now apply this right here, that is you apply this term in every expression for this. What you will get? You will get is equal to in dA minus A dot n dA, B dot n dA, C dot n dA. From here, we now take the dA as common. Sorry. This is summed over for all of the surfaces there, and in overall common we can take the dA, as common. Now we can get this expression, we derive this expression. So you understand that this expression in the bracket, this is the expression for the sum of the surface forces, that is itself a vector quantity. Therefore, we can take that vector quantity and divide it into components, I, j, k components. We simply do that. That we take the ith component of the value inside the bracket. That will give the force component in that ith direction. Okay. So let's just write it in the index notation where the force is taking in the ith direction. We write it as now understand there is a dot product there. So dot product is expressed in the index notation as ij into nj. Fine. We get this. Now what we will do? If we get this expression, now we'll not again go into mathematics right here. What we will do, we will take this tetrahedron element only and apply the Newton's second law of motion there. We get the surface forces according to mathematical constant, vectorial constant, geometrical constant. We get that expression in terms of I and j. But we now think about the physical perspective. We apply the Newton's second law of motion. What we can get, second law of motion is mass into acceleration is the sum of net forces. So as right that we are applying the Newton's second law of motion, we get mass into acceleration as equal to net force acting on the element. Fine. So What is this net force? This net force can be surface force and also volume force. Now, surface force is, as we calculated, that is acting at a contact surface. Surface force, that is the pressure, shear force, etc. And the volume force is acting on the whole volume of the fluid element. That is electromagnetic force, electrostatic force, buoyancy force, gravity force, like that. So these are the surface forces and volume forces. Makes total the mass into acceleration. Fine. So we write in terms of mathematical terms. That is again ma equals to Fs plus Fv. Fs is surface force and Fv is the volume force. Now let's understand this. We have taken a small tetrahedron element like that. That is from the Cauchy construction. Let's take a linear dimension. That is, let us take that delta x. That is, delta x is the linear dimension of the tetrahedron element, and we now shrink this delta x, or let's say we shrink the tetrahedron volume to very little, or very little volume, or tends to 0. So actually we are shrinking this linear dimension delta x to 0. That is, limit delta x tends to 0. So what we will get now? You will now understand this ma acceleration, sorry, mass into acceleration. Okay. Here acceleration is a finite quantity. Acceleration is not becoming infinite anywhere. So how the mass will depend? It is equal to rho into volume, density into volume. Now density is again finite. For local density, acceleration and density can be finite. Okay. Now what is this volume? Volume, as you can understand, that it is simply proportional to that volume element delta V, which is an order of delta x cube. Any volume element is in the cubic order of the linear dimension. Okay, so that we can get for the mass into acceleration part, that the mass into acceleration whole will be order of delta x cube. What about the surface force? It is acting on a surface. So surface force will be proportional to a surface element, that is delta x square, and the volume forces, it is again proportional to my volume. So it is again be proportional to some volume element, that is delta x cube in the order. Now what you can tell? As I am telling that delta x we are tending to 0. In that case, this is a clear mathematical concept from the order of magnitude analysis, that delta x cube will fall very faster than delta x square. Let's say delta x cube is the order 10 to the minus 3. So cube will be 10 to the minus 9, but the square is 10 to the minus 6. So the volume is about 1000 times smaller than the surface forces. So we can exactly neglect that in terms in front of the surface force. So what finally we are getting is the, from the equilibrium equation, sorry, that is 0 equal to Fs plus 0, or Fs is equal to 0. That is the net surface force acting on the tetrahedron element is 0. Therefore, for that Cauchy element, the surface forces just balance out to 0. So what this is from the mathematical or and the physical concept of the tetrahedron element only. So what now we can get? This is my surface force into delta A, just delta A is not equal to 0 anywhere. So this is the quantity for my surface force, the underlined, this one. So this quantity is 0. because delta A is not 0. If the delta F is 0 or F is 0, so my quantity in the bracket is 0. So we now just equate it to get the final. Okay. Let's just write the equation first. Okay, write it there. Okay, we get like this. Fine. Now let us understand what is this sigma in or the component in the left hand side. This is the component of stress acting on surface delta A with area normal n, and we are taking the ith component of that. Fine. So this is the component of the stress, and that is equal to this whole quantity, which can again be written as Nj. So what can we tell from this last expression? That is, we are getting on the left hand side a component of the stress, the ith component of the stress acting on the area normal with Nj, and we are getting a quantity in bracket only in terms of I and J, and after we get the Nj, that is the area normal. So the quantity in the bracket that we underlined has nothing to do with that area normal. It can be anywhere. If we want to take the component, that is stress component, with the area normal, which is on the area which is area normal Nj, we multiply that component, the area quantity in the bracket, with the area normal Nj. Okay, so what we are getting, that is sigma n on the right side, sorry, the left side of the equal sign, sigma in, and the Nj, or here just consider as sigma and n, are independent or arbitrary of the choice of axis. This is a very critical point here. That is, let's say I have taken, in case of ij, in case of the aj, bj and cj directions, let us take a different set of orthogonal directions. Let's say a prime j, b prime j and c prime j. But if my area normal has a fixed direction, we can again multiply it and we get the same fourth direction, same stress tensor, or the stress tensor I am using the term not, but the stress quantity. Okay, so my stress quantity is independent of the choice of axis there. Therefore, let's just define it, that this quantity as the quantity in the bracket as sigma ij, and because it, as you can understand, it has both indices I and j, so we can write sigma ij as I into aj plus b into bj into cj, and we can write this thing as sigma ij into nj. This is a very important expression. So what are we getting from here? This nj is the direction of area normal. This is my traction vector acting, I mean, this is the stress quantity acting on the n We get the traction vector, the ith component of that, we multiply with the delta A to get the surface force, as simply we reduced for the earlier case. So what is this quantity there that is multiplying with that? This is the stress tensor, which depends on means which has the information of the direction of force acting on the area with area normal n. So let's just again write this clearly here, that sigma ij is the stress tensor where this ith component gives me the direction of force, jth component gives me the direction of the normal, but itself is not dependent on that normal. It gives the direction of that normal. That is, what am I providing as the area normal, that is nj. It multiplies with j, that jj is, you can understand, that is repetitive index. So for index notation it will summed over, and we get the value for the ith quantity of the force, ith component of the force. So we get this from that simple tetrahedron element or Cauchy construction. Thus here sigma ij is the ith component of the force per unit area exerted across a plane surface element is normal to the j direction. Now there are two more points I want to add regarding the sigma ij or the stress tensor. As you can understand, again I have explained it already, that is the local stress, that is sigma ij, is independent of n. As I again explained, that we take any n and I multiply to get the traction vector and again the surface force. So the sigma ij is independent of n at a particular point, or in the domain it is independent of the normal vector, and also this is fixed for a particular x and t, because okay, let me draw like this, as we have drawn for the again I am drawing the Cauchy construction here, that is the tetrahedron element. Let's consider this as any fluid element at x and t. This x is the overall space domain x, y, z, and t is the time domain, as you can understand. So let's just consider that fluid element at a particular space and time with specified x and t. The sigma ij will be fixed for that particular x and t. That is, it is a local quantity sigma ij. This is not any global. This is a local quantity sigma ing. A stress tensor is local for that particular space and time. And this is the stress tensor. Okay. Sir, as sigma ij. Now we will prove that this sigma ij or the stress tensor is symmetric. So let's just go there. Here. Okay, fine. So we have to now prove stress tensor. Sorry for writing there. Is symmetric. This will now prove. What is this? I mean, what is the mathematical expression for that? That is sigma ij is equal to sigma ji. That is irrespective, I mean, that the ij can be interchanged here. So for proving this, let us take, again, this is the orthogonal axis. We are now taking any arbitrary fluid volume or a fluid element whose volume is V, the surface is S, and above this surface we are taking a point P where a force is acting as dF and the area to that is the radius vector to that is r. So at point P, a surface force dF is acting. The radius vector of the point P from the origin is r. Simply. Now, if we just zoom this force acting portion, we will get like this. That this is my area element or the surface element where the force is acting like dF. The normal to the surface is n. The area of this surface, let's say I am considering it as dA. This is a surface force. This is not any volume force. This is a surface force. Okay. So now we calculate the moment of this surface force. The particular moment for this surface force. What it will be? It will be dm equal to r cross df from the simple cross notation. Now what it will be for the whole fluid element? This is for the single surface force, df, elementary surface force. Now what it is for the whole fluid element? It is just the surface integral of that, that is m is equal to surface integral of my r cross df. Now if we write this cross product in terms of the index notation, what it will get, what we will get, that is we will integrating over the surface S. For the cross product, epsilon will come, epsilon ijk into rj. Now this rj is for that radius vector part at rj. This is the component. Now for the df, this is the surface force. Now as we explained from our previous Cauchy construction part, that the surface force is equal to a stress tensor, that is a, let's consider a traction vector, into some area element, which can be further decomposed into the stress tensor, into the area normal, into the area of that surface. So what it will get? We will get as sigma ke into ne into dA. This is whole is the dF, stress tensor part, area normal, dA. E is the normal direct, normal. I mean that this E is for the summing, that sigma ij into nj as we did. This is the same part, that is the ne is the normal vector and E is the repetitive index there, it will summed over, and k is the kth component for that force. That is the dF acting as simply. Fine. Okay. Now, as you can understand, this is an area integral. Now we can convert the area integral into volume integral using Gauss divergence theorem. Therefore, we apply the Gauss divergence theorem here. So we apply using Gauss divergence theorem. What am I getting? Sorry. From this expression, we will get is equal to integral again over volume epsilon ijk. Divergence gives me what? The divergence of this quantity. Now divergence of this quantity will become in index notation as delta by dou re into rj into sigma ke, this is k, sorry, into dv. Simply here re is the that coordinate axis that we are taking, and we are taking divergence over. That is fine for that. So using chain rule, now we can write it as, with chain rule we just again decompose it as epsilon ijk into delta rj divided by delta re into sigma ke plus delta sigma ke divided by re into rj. Very simple. Now, what is this? Dou rj by dou re. This is nothing but the Kronecker delta of Je. That is, you can understand when Rj is in the same component as Re, it will become 1, otherwise it will become 0 as we're taking the partial derivative. And simply it is just because just become the Kronecker delta symbol delta Je. When J equal to A, it will become 1, other else is 0. As simple as that. So we can write it as I'm writing here the volume integral of the epsilon ijk. Okay, so here is again that when we are taking delta Je into sigma ke as the E is the repetitive index, this will turn to a again simplified form as simply sigma kj. This is just a index notation. Sigma ke divided by re integrated over dv. Now let us take the first part as 1 and the second part of the integral as 2, or the whole integral first part as 1 and the second part as 2. So let's now analyze this 1 and 2 part separately. Okay, let's explain here that 1 is integral v epsilon ijk into sigma kj into dv. Part 2 is integral v epsilon ijk into rj into ke divided by re into dv. Okay, so these are two different integrals. Now let's again, as we did for the Cauchy construction case, surface force and volume force, we did the order of magnitude analysis. We do it for the same case here. Let's say then, okay, here again, this is a good mathematical assumption. Also from the physical perspective, this is also true that my sigma kj is a finite quantity, the stress tensor, and also the gradient of stress tensor is also a finite quantity. This is the local quantity. This is not become infinite like that. So this is a finite quantity. Okay, so we not bothers about that. So there, then what is the order of magnitude for the first integral? It is only dependent on the volume element. So it is the order of that volume element because this is finite. What it is for this quantity? You can understand. This is the finite part, but what is Rj? Rj is the radius vector or the radius component of that. So radius component is simply v to the order of v to the power 1 by 3. Clearly. And the volume element itself is the order of v. So therefore the whole integral will become the order of v to the power 4 by 3. Fine. Now, let's say again, as in the first case, we shrink the tetrahedron element. Again, for this case, we are shrinking that small fluid element. So the volume of the fluid element is V. We are shrinking that. So in the limit where V tends to 0, what am I getting? This order of V to the power 4 by 3 element will decay faster to 0. That order V, this will decay faster to 0. This is true, very true. Therefore, what we are getting that in case of summation for the integrals, this second part of the integral will be negligible in front of the quantity at 1. True. Therefore, for this integral, we can only consider the first part. Okay. So as of now, what we are calculating for the surface force only, that is the moment of surface force. But one may ask, okay, then what is the moment of the volume forces? But that is because that is also present. As we did, there are two types of forces, surface force and the volume force, as we know. So then what is the condition about the volume forces? Okay, fine. Therefore, the volume forces is again proportional to my volume, and the moment of volume forces is proportional to radius into volume. Aren't you getting any similarity with this term? So these will again become order of v to the power 4 by 3, the moment of volume forces. Therefore, if we take the moment of surface forces plus volume forces, the surface forces moment will simply become the first integral. And also this volume force moment is similar to this term too. That will again tend to zero faster. So what are we finally getting? We are finally getting that the net moment is equal to integral epsilon I j k sigma kj into dv. This is an excellent simplification of the existing problem. We just shrink the volume delta v to the volume element v to 0. We get the moment as simply in this expression. Now understand the physical perspective again. That is, what is this moment? This moment is the internal moment of the fluid element. That is, different surface forces are acting, different volume forces are acting, and we take the moment out of that. So that is the internal moment for that fluid element that exists for the all fluid elements. Now what we can understand from the physical perspective, that if that fluid element can stretch, the fluid element can compress, extend everything. But for the most fluids, there is no internal moment. For the itself fluid element, the fluid particles are not creating moment inside the fluid element. There is an overall moment. Let's say there is a vortex flow like that. In that case, there is an overall moment for that. But for each fluid element, there is no moment. So unless it is this is a special example. Let's say we consider the ferrofluid. So for ferrofluid, it can happen that we apply a magnetic field. So the fluid particles inside that fluid element can align according to that, and it can generate a net moment inside the fluid element. But there is no directionality or the align in this fluid element. This is for general any fluid. Therefore, for most of the fluids, there is no internal moment. This is a very important point. There is no internal moment. Therefore, for most of the fluids, m is equal to 0. So this equal to 0. So from there, what we can get? That is integral v epsilon I j k sigma kj equals to 0. Sorry, there is also a dv is equal to 0. Now again, understand this integral. That what is this dv or what is this volume? Is the choice of this volume is totally arbitrary. We can take any other volume from a different fluid domain and from a different fluid part. We take any other fluid element with any other volume of dv. But for that case also the moment is 0. So this is again from the mathematical part, that the moment being 0 is not dependent on the choice of that fluid element or the choice of the dv. volume, because the choice of volume is arbitrary. So when the integral is 0, where the choice of the integration on the domain which is happening is arbitrary, so therefore there is only one option left. The integrand itself is 0. So from there what we can get is epsilon ijk sigma kj equals to 0. You solve this by applying for okay. You solve this for applying different I, j, k. You apply the values when I equal to 2, I equal to 1, j 2, k 3 in circular cyclic order. It will become 1, else it's -1. When it is repetitive index, there is a 0. So we apply this, we can simply get sigma kj equals to sigma jk. This is an important part. This is nothing but the stress tensor is symmetric. We proved we are taking the moment of the volume forces of the net fluid element, the volume forces, surface forces, we take everything, we equate it to 0, and we get sigma kj equal to sigma jk. Therefore, we proved that stress tensor is symmetric. Okay. So we proved that stress tensor is symmetric. Now we will find what is the property of the stress tensor, or what the stress tensor takes the value when the fluid element is at rest. Okay, so now we will find that. Let us take this here. Okay. So what is the stress tensor for a fluid element at rest? We know as of now, just take a particular point sigma ij, a stress tensor that is for the 3-dimensional. We get a 3 cross 3 matrix, that is 9 elements. But as you know, from the eigenvalue decomposition or the principal axis directions, that we can represent any matrix that is happening here in its principal directions, that is its eigenvector directions. And what are the values for that? We get the diagonal matrix, where the diagonal values are correspondingly the eigenvalues. So in the same way, we can represent this stress tensor matrix. This is simply a matrix. We can simply represent it in its orthogonal directions in the principal, in 3 orthogonal directions, the principal axis, and the values correspondingly, that is the principal stress values, which are sigma I11 prime, let's say sigma 22 prime, sigma 33 prime. Then the non-diagonal terms will simply become 0. As you understand, we are representing in the principal directions. So first we choose the axis of orthogonal directions as the principal directions or eigenvector directions, and we write the stress tensor along those principal axes, as accordingly you can see where these are the principal values of stresses. Okay, so again what I am doing, this is now clear that sigma ij can be written as this diagonal matrix. Now again we are writing this diagonal matrix as a summation of 2 different matrices. We are considering one matrix as this you can understand sigma ii, this sigma ii as it is a repetitive index, so it will summed over the dimension, that is sigma 11, sigma 22, sigma 33 plus this, have to write the remaining part for that. This is clearly understood. We wrote this sigma ij matrix first in terms of the principal directions, in terms of principal stresses and diagonal matrix, and we write the diagonal matrix again subdivided into this matrix where each of the diagonal elements are equal, and then this matrix where this is not equal. Now we can say some subtle points about the properties of these two matrices. What is it? Because you can understand, if we take this common, this will become sigma ii into some I. This is the identity matrix, diagonal one. Fine. Therefore, what can you tell about this matrix particularly? That the first part, we can say, this is an isotropic matrix. Why isotropic? This is rotationally invariant, as this is an identity matrix itself. You can rotate it in different directions. The value of this matrix will be, the value means the matrix will remain same with the scalar value as 1 by 3 sigma ii and identity. So it is rotationally invariant. Therefore, it is an isotropic matrix. So I am writing that is, it is an isotropic matrix. It is same. It will be same in the spherical symmetry. It has a spherical symmetry. It is same in all directions. Fine. Now what is the second part? Second part, as of now, it is simply a diagonal matrix, that is fine. But there is another property. If you find a trace of that, it is simply because 0. Because again, sigma 1 1 prime plus sigma 2 2 prime plus sigma 3 3 prime is equal to sigma ii, because sigma ij equal to that, so that trace will be equal to that trace. So we get this. So this is a traceless matrix. This becomes isotropic and a traceless. We call it a deviatoric part. That is, we consider the sigma ij, we construct the sigma ij as an isotropic part and a deviatoric part. Fine. Now understand the physical aspects of this isotropic and deviatoric separately. What we told about this isotropic? This isotropic is rotationally invariant. Therefore, if we consider a fluid element a spherical symmetry, or if we consider 2D, then it's a circular fluid element, then the forces acting on it, because as you understand, the stress into my area will give the forces with the area normal. So accordingly, if my stress is uniform, is equal in every direction, therefore the force from the every direction is always be equal, because the unit normal is unit normal and that is equal and rotationally invariant. So whatever the values you take in different directions in the 3D domain, it will give the same value. Therefore, if we just understand it is in the 2D, that we draw a fluid element like this, then the forces acting on it due to the isotropic part will be symmetrical. In case of 3D, spherically symmetrical. In case of 2D, circularly symmetrical. So it will be acting like this. From any of the directions, any of the radial direction, and that if you take any angular quantity theta that ranges from 0 to 360, the force will be same. Therefore, a uniform and equal distribution of forces is all throughout that fluid element. Therefore, if we apply, now you try to compress this fluid element by applying same forces from all of the directions. Now forces from all of the directions will simply just cancel out. What it will give? It will give a fluid element, that this fluid element which can resist deformation. This is a very important point, that this fluid element can resist deformation, because the forces acting on different directions is simply cancelling out. There is no net forces. Therefore, it will resist deformation. It will stay at that place only because the force is isotropic. Now, what about the deviatoric part? For the deviatoric part, you can understand that it is traceless. So as of now, we are considering as a 3D matrix, 3 cross 3 matrix with 0 elements here. If we just shrink it to in 2D, what is the 2D analogy of that? That if it is traceless, then sum of this and this is equal to 0. Therefore, it has equal and opposite parts, but acting in two different orthogonal directions in 2D. In 3D, you can understand. In the 3D, you can understand from three different directions. The forces will be such that the sum of them is 0. But for 2D, is easy to interpret there. So let's say the forces acting in the vertical direction is like this. Therefore, in the horizontal direction, the forces will be just equal in magnitude, but opposite direction. Therefore, if it is acting as compressive forces in the vertical direction, extensive forces or tension forces will act in the horizontal direction. Therefore, an equal but in opposite direction of force is distributed over this fluid element for the deviatoric part. So from the physical perspective, what you can tell? As soon as this force distribution is acting on the fluid element, it cannot resist any deformation. It cannot resist deformation. It will simply be stretched towards the horizontal with being, that compressed in the vertical direction for the deviatoric part. Because as soon as the force starts acting, it will have a continuous deformation. Therefore, from the overall conclusion for this 1 and 2 part, what I can tell that when the sigma ij is acting, if we just superpose the two effects, for the isotropic part, there is no deformation, it can resist the deformation, the fluid stays at the same state, where for the deviatoric part, it is instantly having a heavy continuous deformation. It cannot resist. Therefore, again, we consider the physical aspect, that to remain the fluid at rest, it should not have any deformation. It is at rest. The every force is balancing each other. So what is it? This is nothing but simply the isotropic condition. Therefore, the fluid element to remain at rest, the deviatoric part must be equal to 0. There should not be any deviatoric unless it will again start deforming. So from the sigma ij construction, we can tell that this deviatoric part is simply 0 and the sigma ij is purely isotropic. Here is the conclusion that sigma ij equals to 1 by 3 sigma ii into I. This is isotropic. Therefore, for the fluid element at rest, the stress tensor is isotropic. This is proved. Fine. Now, there is another you can understand from the physical perspective again, that if this is the fluid element and the forces is acting equally in from every direction like this, this is nothing but the pressure forces acting on the fluid element. Understand from the physical perspective, this is nothing but the pressure forces that is pressurizing the fluid surface equally and opposite, equally from every direction and balancing out. So there is the relation between the fluid element at rest, the stress distribution over it, and the pressure force, which is deduced as minus P delta Ij. Ij again Kronecker delta, so it is only acting in the orthogonal direction. I mean, you can understand there is no the non-diagonal part. It has only the diagonal part. It has so the pressure and it is acting in the opposite direction to the area normal on this surface. You can understand the area normal this side and force is acting on the opposite side. There is a minus sign. So sigma ij is simply equal to minus p into delta ij. Therefore, we can write that P equals to minus 1 by 3 sigma ii. from this to equal, if we equate this to, this is the static fluid pressure. When the fluid is static, when the fluid is at rest, the pressure at a particular point is constant and it is equal in from every directions, spherically symmetrical, and it's equal to the minus 1/3 of the trace of the stress tensor there. Clear that part? Now, as a final conclusion, what can I tell about the stress tensor? That stress tensor sigma ij equals to minus p delta ij plus dij. This is in general. This is not for fluid at rest. This is in general. That in general, we construct an isotropic part, that is nothing equal to pressure part, and a deviatoric part. For a fluid element at rest, this deviatoric part is 0 and the sigma ij is only equal to this pressure part. But in general, there is in motion, the fluid element is in motion. For that part, the stress tensor will have isotropic as well as the deviatoric part as non-zero. Okay, so we got the expression for the stress tensor. Now we will derive the equations of motion of fluid for a fixed control volume in space. So let's take me another area. Okay, fine. Let's do it here. Just a minute. Let's take this a new area. Okay. We will now derive the equations of motion. This is a very important part, and this will lead us now to the path for the derivation of the Navier Stokes equation. So let us take again a set of orthogonal axes and let us fix a control volume here. This is a control volume. This has a fixed volume entity and it's fixed in space. Now, as you understand, that is, this is a fixed quantity in space. So therefore, fluid is entering and fluid is outgoing from this volume element. This is the volume V. It has a surface area of S, and let us take a surface element right here, and let us draw this. That okay, I am zooming a bit here to understand it clearer. This is my surface element where this is the area normal for that surface element. I am zooming just right this. This is the area normal. Velocity is getting out from this surface element from the control volume with velocity u and in this direction. And let's say the area of this is ds. The differential area of that. This is just simply ds. Fine. Now let us define a fluid property, any fluid property. We are deriving the conservation principle first. So let us derive any fluid property. We'll write the conservation principle according to. Let us take it as theta. This is any fluid property. It can be, let's say, momentum, it can be energy, it can be mass, anything. This is any fluid property. Now, this is the important mathematical part, that we now write the conservation principle of that fluid property in this control volume. And for doing that, we will be invoking, we are using the Reynolds transport theorem. Okay, so we are writing the conservation principle for theta in that fixed control volume using Reynolds transport theorem, RTT. If we do that, what we will get? We will get the rate of change of that property for that volume, that is we can get by integrated over the whole volume, is equal to the integral of the partial derivative of that fluid property integrated over the volume plus a surface part, that is theta u dot n into ds integrated over the s. Now you have to understand this very clearly, that this d by dt of the theta dv, we are integrating over the control volume where the differentiation sign is outside of the integral, and integrated over the volume means we are taking the whole volume there, the fluid property for theta. That can be written as using Reynolds transport theorem, or that is again the higher dimensional analogy for the Leibniz integral rule. That is, we take the differential inside by partial derivative delta theta by dou t dv integral with a flow property, that is a inflow minus outflow kind of thing. You can understand, that is u is getting out of the n, but in the opposite side you can enter the fluid element. In that case that will be an inflow and this is an outflow. So if we integrate that u dot n part over the whole surface, we can get the net outflow minus inflow, that quantity, because that is the rate of change of property. So this is the mathematical. Let's understand the physical part of it. That what is the rate of change of a property in a volume? Number one, now this is a flow property. So something is going in, something is going out of that control volume, because that is in fixed in space. That is not moving, that is fixed in space. So something is going in, something is going out, that can be any property. That property considered as theta. Fluid is going at velocity u. Therefore, the rate of change of that property inside that control volume is equal to the local change, that is the dou by dou t part, dou theta by dou t part, that is the local change of that property inside the control volume, with there is the local temporal in the temporal sense. I mean, local temporal means at a temporal sense, that is having, because you can understand that theta is a function of both space and time. We're only considering the time part there in this first expression after the equal sign. Okay, and the second part is the flow property, that is something is going out, something is going in. If we consider them, that also corresponds to my rate of change of that property inside the control volume. So rate of change of the property in the control volume is the summation of the local temporal change of that in the control volume with the flow change of thing. Because there, let's say, consider a situation where is nothing, the inside control volume part is steady, that nothing is changing, but fluid is going in and going out. So there is something change of the net change of this property inside the control volume. So that is being represented in this equation where Reynolds transport theorem is also invoked, and this is the conservation principle for the theta. Fine. This is a very elegant mathematical construct. From here, this is the integral over the volume. This is an integral over the volume. This is the integral over the surface. We want to consider the integral over the volume for that part also. What we can do? Simple, Gauss divergence theorem. So using divergence theorem, what can I get is, I'm writing only the second part, that is equal to integral v delta dou theta by dou t into dv plus integral v divergence of theta u dv. Simple. This n is the normal, and ds part becomes the dv, and the inside the theta u becomes the divergence of theta u integrated over dv. Now I should write here. So from this expression, using the chain rule, simply we can write as integral v dou theta by dou t plus u dot grad theta plus theta grad dot u dv. Fine. Now you can understand that this first term, what is this? This is nothing but the material integral of theta. Fine. So what we can write, because from that what we have written in the left hand side as equated and simplified. So sorry, the d by dt, this should not be here. Yes, d by dt of theta integrated over dv is nothing but volume integral of capital d theta by dt plus theta grad dot u dv. We get this simplified expression. Fine. Now here is mathematical substitution we can apply. Let's say in case of theta, we apply rho theta. Nothing will change. The theta is substituted to rho theta. Yes, we can apply because this is the fluid property. If we apply the rho theta, it is again another physical quantity, because in that sense, if you can understand the volume integral of rho, you can get the mass of that fluid element. So we just substitute theta as rho theta. Then what we can get? We can get that d by dt volume integral rho theta dv equals to volume integral d rho theta by dt plus rho theta grad dot u in the dv. Again, using chain rule, use the chain rule for this part and dissociate it. We can get equals to volume integral rho d theta by dt plus theta d rho by dt plus rho theta grad dot u dv. Fine. Now again another simplification. What we can get? Let's just take it here. See this. If you take the theta common, it will become d rho by dt plus rho grad dot u. What is this? This is nothing but the continuity equation for the control volume, which we can derive from the control volume, the continuity equation. So from the continuity equation, this is equal to 0, or simply the mass conservation rule, this is equal to 0. So what are we left with? We are left only with integral v rho d theta by dt integral dv. Fine. Now let's just take it here. We know the left hand side is this and the right hand side as we get as this. Therefore, we do another substitution. We now take theta is equal to u, that is my flow velocity. We can substitute, this is a physical quantity, we can substitute there. So after substituting, what am I getting? Getting d by dt integral v of rho u dv equals to volume integral over v rho du by dt dv. This is an excellent simplification from that conservation principle, where when we apply u, then what is rho u? Rho u is nothing but momentum, or momentum per unit volume, you can understand, but that is fine. Or momentum, if we integrate over the volume, we can get the momentum. So as a simplification, what are we getting? We are getting this as rate of change of momentum of the fluid element, that is control volume that we have taken. This is the rate of change of momentum. Now using Newton's second law, what we can write? Rate of change of momentum of any fluid element is equal to the summation of body and surface forces on that element. Simply, mass into acceleration equal to force, and that is equal to rate of change of momentum. So force, net force acting on the fluid element, net force can be subdivided into volume force and surface force, that is body force and surface force. So rate of change of momentum of the fluid element is equal to summation of body and surface forces acting on that element. So what are those body and surface forces? Let's just understand that. Now what we can write, that dt, and also simply, as you can understand, this is the rate of change of momentum, that is force. We can take the ith component of that. Therefore, using the ith component vector quantity, we use the index notation, rho ui dv equals to rho fi dv volume integral plus s sigma ij nj ds. Understand this. This is the rate of change of momentum, that is equal to my volume force. This is rho density. Fi is the force per unit volume that we are getting. Fi in the ith component, but that is fine. And sigma ij into nj. This is, again, you can understand, that is the surface force, where sigma ij stress tensor in the area normal into area, nothing but surface force integrated over the whole area. You get the net surface force for the ith component. Fine. Or again, we can write in simplified way, because this left hand side, as we have proved from the conservation principle, is equal to this. We substitute this in equation and we can get, or integral v rho dui by dt dv equals to rho, that volume integral of rho fi dv plus volume integral of sigma the dou sigma ij by dou xj into dv. Now again, I have added another mathematical formula there, which is, you can understand, this thing is an surface integral. So how to convert surface integral to volume integral? Again, apply Gauss divergence theorem. That will give the divergence of that, and divergence can be written in terms of index notation as a repetitive index as j here, as dou sigma ij by dou xj. We can get this expression. Now again, understand that part. Here actually we can take every part in the volume integral, in the everything is in volume integral. So every part in the volume integral we can take in common. So it will become some integral into some part dv equal to 0, as you understand. But here also the choice of the control volume is taken as an arbitrary. It is fixed in space. It is a fixed volume entity, but the choice of that control volume is arbitrary. We can take any control volume from the fluid domain. But for all of the cases, if this integral satisfies to 0, therefore what we can write, the integrand must be 0. So if we take the integrand or the common out of that, what are we getting as a very simplified expression? Rho dui by dt equals to rho fi plus dou sigma ij by dou xj. It got a slightly skewed, but that's okay. Sorry, it got okay, fine. So this is what we know as equation of motion in a control volume. This is the equation of motion for that control volume in space, where we are relating the rate of change of momentum here equal to the surface forces and also the volume forces. Now understand from the physical perspective again that we want to know from the equation of motion what is the force acting, what is the momentum, what is the velocity, like that. So rho dy by dt we want to know. From volume forces we know there is gravitational forces, there can be some electrostatic forces, electromagnetic forces, everything, but not considering here. But from that field data we can get the Fi, that is force per unit volume. But what about the last quantity, that is gradient? Sorry, as it is understand, the divergence thing or the rate of deformation tensor, that is dou sigma ij by dou xj. Sigma ij is the stress tensor, but not we are considering the the divergence of that. Sorry, I am talking the gradient. So we are taking the divergence of that. So what is that quantity? We have to understand that dou sigma ij by dou xj, what is that? Fine. So our next part will be related to that only. Let us take a new part again. Okay, let's start from here. That we get, that we want to know dou sigma ij by dou xj. What is this? So from the previous formula that we derived when we proved that stress tensor is isotropic for a fluid element as rest, there we came to a final expression that sigma ij equals to minus p delta ij plus dij. Now again, if we know the stress tensor, we can apply accordingly, we can get the mathematical construct for its divergence and we get that dou sigma ij by dou xj. So we have to understand that sigma ij totally first, and this is one part is isotropic, that is pressure. This is simply pressure, we can measure the pressure. But what is this deviatoric part? So as you can understand from deviatoric part, one, the pressure is the normal force or it is the normal stress part. But deviatoric part is the shear stress part. That is the counterpart of this normal force, where the stress is composed of the normal and the shear. So that is the shear force part, Dij. Sorry for that. So fine, Dij is the deviatoric stress. And also now again you have to understand the physical aspect of this, that this is the related to shear stress. Now from Newton's law that law of viscosity, you know that let's say the fluid is like that, that the profile of fluid is like that. So what is the shear stress here? Shear stress equal to mu, some coefficient of viscosity we will come, but here according to Newton's law of viscosity, du by dy, so that is related to the local velocity gradient, not divergence. It is related to local velocity gradient, du by dou u by dou y. Similarly, from the same physical analogy, what we can tell that this deviatoric stress is also related to the local velocity gradient. That is, dij is related to my local velocity gradient. Let's say consider duy by dxj. We consider now this constant of proportionality as, let's say, dij equals to some aijkl into duk by dxl. This is a mathematical construct again. That is, what is this aijkl? You understand now this velocity gradient for a three-dimensional field. It is a 3x3 matrix. The deviatoric part, shear stress part is also a 3x3 matrix. So Aijkl is the connecting of that two second order tensor Dij and the gradient. Connecting Aijkl is a fourth order tensor. So this is a fourth order tensor. Fine. As of now, this is clear. Now we can explain it again from some physical perspective that let's say there is some fluid element. Now what is the shear stress acting on that? This is related to the relative velocity between this. So that also relates to the that deviatoric shear stress is related to the relative motion of the fluid elements, and that generates the deviatoric shear stress, and thus relative motion is also related to the local velocity gradient. So we get this. Fine. Now you have to understand this part, that what is this Aijkl? 3 cross 3 cross 3 cross 3, this is a fourth order tensor. So we can't just simply go with that. We have to simplify it. How? So here we are assuming the fluid is isotropic. Now what is an isotropic fluid? You have to understand this very clearly, that we are assuming that the fluid is statistically isotropic. This is a very important notation for that fluid, that fluid is statistically isotropic. That is, the deviatoric shear stress generated in an element of the fluid by the velocity gradient, as you can see here, is independent of the orientation of the element. This is independent of the orientation of the element. I mean, I think you can get some relation, that when we express that sigma ij as some isotropic part and deviatoric part, we can what we told about I, that I is the isotropic part and it is rotational invariant. It doesn't depend on the which direction I am pointing, it is same in all. From the same analogy, the Aijkl or the Dij, deviatoric part, is direction invariant. It is coming. That is, deviatoric shear stress generated in an element by the velocity gradient is independent of the orientation of the element. It can orient in a different direction. That is isotropic fluid. That is not any isotropic matrix. We are not considering isotropic matrix there. Dij is not an isotropic matrix. But for isotropic fluid, the fluid is isotropic. The deviatoric shear stress generated by the velocity gradient is independent of the orientation. Now, what is the statical isotropic fluid? Generally, all gas. So I will write this, that most of the all gas and most of the simple fluids are isotropic. Right, all gases and most of the simple fluids. What is the simple fluids? Water. A good example is water. Now, where it can't be applied? Complex fluids. Now, what is complex fluid? Let's say the complex fluid is some chain of polymers. That is, there is some directionality. Okay, let's say this is the chain of polymers. We can draw. Fine. Now, this chain of polymer can sometime be bent in like a structure like that. What we can get, that this is a structure, this is from there and this is coming. So there can be a velocity here, there can be velocity here. So due to the chain of polymers is arranged in this fashion, the shear stress generated here is related to directionality, because it is moving in a particular direction and shear stress is only generated due to that movement in that direction only. It is not generated in other directions. So there is a directional performance of the shear stress, and it happens in case of very long chain of these uh, polymer molecules. So this is the complex fluid, or let's say we consider any viscoelastic nature of the any fluid, that is also complex fluid. So these are not simple, but for simple fluid it is statistically isotropic. Therefore Dij is directional invariant, becomes invariant, not directional invariant in that sense, it is independent of the orientation of the element. So what we can get, that if it is independent of the orientation of the element, therefore Aijkl is an isotropic matrix. Again, I am emphasizing this part. Dij is not isotropic. Deviatoric part is not isotropic, but it is independent of the orientation of the element. Therefore, the value we are multiplying with the velocity gradient, that must be directional invariant, that must be isotropic. But local gradient has some directional property, local velocity gradient, but we are multiplying with a orientation invariant quantity, that is Aijkl, or directional invariant quantity, that is isotropic matrix. We are multiplying isotropic matrix and we are getting that. So now if we change the orientation for the same case, if Aijkl is isotropic, if we change the orientation, the multiplication will happen, but it will give the orientation invariant Dij. Again, simple, it will give the same Dij. So that is the concept here, that from that perspective is the fluid is isotropic, fluid is statistically isotropic. We can write this quantity Aijkl as a isotropic matrix. And also it is a fourth order tensor. So it is a, we can consider it a fourth order isotropic matrix or a fourth order tensor. Now Aijkl, as there are four indices, fourth order tensor. Do you remember what was another second order isotropic tensor? That is Ij, delta Ij. That is 10001. I mean, this is not, it is not, we consider not like matrix, not considering a matrix form. Let's just consider like that, that if my delta Ij, so I equal to j, in that case it will become 1, otherwise 0. Not writing the matrix here. So delta Ij was the simplest second order isotropic tensor, and Aijkl is a fourth order isotropic tensor. So if we want to create a fourth order isotropic tensor from a second order isotropic tensor, what we can do? Now, understand this very clearly, because this is the purely mathematical part again, that we can write a different combinations of delta Ij, that is delta Ij into j into Kl, delta Kl. This is becoming a fourth order tensor. Okay, because there are four indices, and accordingly if I equal to j and k equal to l, only if that happens, only in that case this will become 1, otherwise every time it is 0. So this is also a fourth order isotropic tensor. But now you can say there are other combinations too. Yes, also there are other combinations. This is one combination. Another can be IL delta JK. Another can be delta IK delta JK. Sorry, this is L. I am very sorry for that. Okay, fine. So these are the possible combinations of the fourth order tensor created from a second order tensor, right? So what can I write from there? We can simply write Aijkl as the linear combinations of this existing fourth order tensor. because aijkl has to be isotropic, and there are three possible situations where it is an isotropic fourth order tensor. So we take the linear combination of all, it will again become an isotropic tensor. So we can write it as, here this is a constant because we are taking a linear combination. Fine. So we have written ijkl as a linear combination of all possible fourth order isotropic tensor. Right. So now what we have derived, I mean we have derived it earlier also, that dij was some diagonal matrix with 0 in the other. So this is a symmetric matrix. This is not isotropic, this is a symmetric matrix. Therefore, here also Dij equals to Aijkl into the local gradient duk by dou xl. This is symmetric, everything. This whole left hand side, right hand side symmetric in Ij. So we can interchange I and j as it is symmetric. So if you interchange this I and j, what you will get? You will get now mu double prime, sorry, oh sorry, I am really very sorry for that. It has to be ji, yes, now write kl plus mu dash jl ik plus mu jk il. We interchange I and l. This will be equal to, again we interchange ji l. We get two equations. We subtract this. So take a phrase again. After subtracting, what we get, as you understand from there, that mu minus mu dash, because the mu double dash terms cancels out to 0, delta ik delta jl minus delta il minus delta jk equal to 0. Now again, you have to understand the mathematical part of that. That this thing, this is, we have taken a constant to add with the linear combination. So it is very unlikely. I mean, unlikely means these are the constant that we have taken. But here, what we have taken is a combination of fourth order tensor, which is dependent on four indices I, J, K, and L. So again, this is very unlikely that this I, J, K, L matches in a perfect fashion, that we get this quantity in the bracket as 0 for all of the cases. This is very unlikely. Not always, because the choice of I, J, K, L is arbitrary. From there we can conclude that mu equals to mu dash, because we have taken as a constant. We have not provided any imposition of constraint on those constants. Now we get the relation that mu is equal to mu dash, and mu double dash has already cancelled. Therefore, we can write now the aijkl as, okay, bring it here. Aijkl, again I am writing as mu, now we can take it as common, ikjl plus il jk plus some, let's say mu double prime with delta ij delta kl. We can easily get this, right? So my box, making a box here. Sorry, that box is crossing. That's fine. That is K and L. Okay. So what we can write from here? Now we can write this mu as coefficient. We are now describing it as coefficient of viscosity. As we get, this is a particular value, constant value, and this is considered as secant coefficient of viscosity. Fine. As of now, it is clear, right? Therefore, what we can write from these two constructions, that Dij equals to Aijkl Tuk by d dou xl. We write again the Aijkl in this format, that mu ik del jl to jl plus delta il jk plus mu double prime delta ij delta kl whole into my tuk by dou uk by dou xl. This is dij, which can be written as, let's just shift it again, which can be written as mu dui by dou xj plus dou uj by dou xi plus mu double prime dou uk dou xk into delta ij. How I get this? You simply can understand that this is the delta. So now equating with that and using proper index notation, we know the delta law, that Kronecker delta, if delta ij I not equal to j, it is 0, delta I equal to j, it is simply 1. Using that formula, we can multiply with that and simplify to get only this expression. Now understand this very clearly. Okay, so this part, what you can understand, dou ui by dou xj plus dou uj by dou xi. This is nothing but a symmetric part. And symmetric part is the deformation tensor. Symmetric in I and j. Because if you interchange I and j, this will remain same. And what is this part? This part is a divergence part. You understand, right? That here is the repetition of index k there. So this is nothing but the divergence. So this is a divergence part. So here you can say if the fluid is divergence-less, this part will become 0. As simple as that. Fine. Now, again, let's say we define two quantities. Let's define it here. I am defining as Eij as half of dou ui, that same expression what we have derived, dou uj by dou xi. Now, what are we going to do? What is this Eij? This Eij is nothing but related to the local velocity gradient. It is related to local velocity gradient. Fine. And if we now apply I equal to j equal to k, if we just apply, we can get from here that ekk equals to del uk by del xk. Very simple from here. Therefore, you use to these expressions, what we can get for delta dij? The dij was this part initially into mu, that was 2 mu into eij, plus there was a delta ij part into mu double dash into delta ij into ekk, right? This is a very important expression where we can represent the deviatoric shear stress. We have represented the deviatoric shear stress in terms of simple coefficients and the local velocity gradient. Fine. Now we can do another simplification. This is again, we know that dij was a symmetric traceless matrix. As you can remember that it was so it was in the format of like this and 0 everywhere. So what we derive that this was a symmetric matrix first of all and was traceless matrix. The trace was summation 0. So if this is a traceless matrix, we have used the symmetric condition. Now we have to use the traceless part. If the if is a traceless matrix dij, so dii equal to 0, that is become d11 d22 plus d33 equal to 0. So you apply I equal to j, what you will get 2 mu ei plus 3 mu double dash ekk equal to 0. What is ei and what is ekk? Both are same. Both are equal to e11 plus e22 plus e33. Cancel out those. Finally, what we get, that is mu double dash equals to minus of 2 by 3 of mu. So we once get mu and mu dash relation using the symmetric condition. Now you use the isotropic, the traceless part condition to get relation between mu and mu double dash. What we get? Mu double dash equals to minus 2 by 3 of mu. Apply this, you get further simplified expression for the dij part. What we get? See, we are getting dij equals to 2 mu eij minus 1 by 3 delta ij ekk. This is the most simplified expression of the deviatoric shear stress path in terms of the velocity, local velocity gradient eij and ekk. Ekk is the divergence part, but that is also in that sense. So therefore, what we can write about our further expression, that is the sigma, that is a stress tensor sigma ij. So let's just take a new page here, new area. We can write as our parent expression as p delta ij plus ij. It is written in terms of velocity gradient. What we can write as sigma ij equals to minus p delta ij plus 2 mu eij minus 1 by 3 delta ij ekk. This is an excellent expression representative of the stress tensor. So we represented stress tensor in terms of the local velocity gradient. Fine. Now what is left? In the equation of motion, you remember why we came here, because we have to find the expression dou sigma ij by dou xj in the equation of motion. So apply that in this and substitute in the equation of motion. So substituting in equation of motion, what are we getting? We are getting dui by dt, sorry, this is equals to rho fi minus dou p by dou xi plus dou by dou xj of whole into 2 mu eij minus 1 by 3 delta ij ekk. This is the total expression. What are we getting for the equation of motion, substituting all of the stress tension notations, the surface force, volume force as expressing a local velocity gradient, everything. This is our very esteemed Navier Stokes equation in most generic form. This is the Navier Stokes equation for isotropic fluid in the most generic form. It is valid for both viscous flow, non-viscous flow, compressible flow, irrotational flow, rotation flow, incompressible flow, everything it is applicable, this set of partial differential equations. Fine. This is the Navier Stokes equation in its most general form. As now, what are we getting? Now, there is a little bit of mathematics left at the last part where we will derive the Navier Stokes equation assuming incompressible flow. So number one assumption as we can take is as mu is constant, the coefficient of viscosity we are considering constant, one assumption. And for incompressible fluid assumption, we can take the rho is also constant. So first let's take one by one assumption. So first take that assuming mu is constant, what are we getting? We are getting as rho dui by dt equals to rho fi minus dou p by dou xi plus mu. It is getting out of the differential 2 into half. This is again a mathematical construct that we can form dui by dou xj plus dou uj by dou xi. We just broken the eij part. Fine. And else what are we getting? Minus 2 by 3. This is the divergence part of xj. Ekk is xk. Fine. Now you apply the index calculations again for this differential, for this partial differential. What we get? That is rho dui by dt dot dt rho fi xi plus mu into del square ui by dou xj by dou xj part, sorry, yes, and another is the 1/3 of del square uj by dou xi by dou xj. Fine. Now our assumption is the fluid is incompressible. Therefore, for incompressible fluid, rho is constant. For a rho constant, what are we getting? I am moving it a bit up again. We are getting for incompressible fluid rho du by dt equals to rho fi minus pi plus mu I plus xj. Okay, what is the change? The change is where this term gone. But that is, you understand, that is part from the divergence. Now for incompressible fluid, we know that, okay, that divergence of the flow is zero. So there is not any, this term is simply equal to zero. If this is zero, I am again taking it a bit. This part is totally zero. This part. If this part is zero, in final expression we are not getting that part. We are only getting the Eij part, as you can understand from there. So you can write again in the vectorial notation as du, that was an index, we can write in a vectorial notation now, rho f minus grad p of Laplacian of u. Fine. You understand that part, that this thing are considering as a Laplacian. So this is the Navier Stokes equation for incompressible fluid. As you can understand that we're getting the rho as constant part, so and also the divergence part is zero. Therefore, we are getting the Navier Stokes equation for an incompressible fluid from our very old that Cauchy construction, then stress tensor, then equations of motion and conservation principles in a control volume. We get everything and we find the Navier Stokes equation. So thus the Navier Stokes equations are derived. Thank you.